Okay, guys, today we're doing 8.1 definite integrals, and we're just going to be looking at graphs today, okay? So it should be a pretty easy lesson. Okay, let's get started. Okay, last chapter we dealt with all Riemann sums, which means we dealt with all approximations for finding an area. As you can see on this one right here, we are trying to find the area from point 0.5 to 3. And we used left-hand Riemann sums, and it looks like it was an over approximation, and it was just an approximation, right? It wasn't the exact area. With an integral, what we're going to be doing this chapter is we're going to be finding the exact area that is encaptured from the function to the x-axis. Okay, and here's how we're going to denote that. This is the integral sign, and it just means the area between the lower bound, which in this case is 0.5, and the upper bound, which in this case is 3. And inside of here, it's going to be talking about the function that's going to be drawn that you're finding the area between the x-axis and that function. Okay, well, let's get started. Today we're just going to be dealing with shapes. So I'm not going to show you how to deal with an actual function yet. In this case, this is a graph of f of x. And you're going to be able to find the exact area between the x-axis and the function because it's all geometric shapes that you guys know how to find the area of. If you're not good with area, let's just tell ourselves or remind ourselves about some of the area formulas that you're going to be using. The area of a triangle, so this is a triangle. It's going to be 1/2 b or base times height divided by 2, or 1/2 base times height, however you want to think about it. We got, in this case, a semicircle, and the area is going to be, so a circle is pi r squared, right? Pi r squared, and then if it's a semicircle, which is just half of one, you're just going to divide it by 2. And that's all you're going to need for this one right here. If you want, you can think about some of these things as being trapezoids, and you should remember your trapezoid area formula because we just did it in Riemann sums. It's going to be height base 1 plus base 2 all divided by 2. I try to break everything up into just triangles and semicircles though, and rectangles. So I don't really try to deal with trapezoids. Okay, so now let's just real quick show what areas we'll be finding because it's from the x-axis to the function. So like on this one, this is negative area. It's all this right here, and that is negative area. And this right here is positive area because it's above the x-axis. And then you got positive area again because it's above the x-axis. And then you got positive area again for the same reason. Okay? So let's start doing these. We're going to find the integral from -5 to -1, which means we're going to go from -5 over here to -1, which is right here. And we're just going to go through and we're going to find that area using geometric shapes. And this area will be negative, this area will be positive. So we'll just subtract the two or add the two together and we'll see what happens here. So this first one, I'm going to focus from -5 to 4 first because I'm going to break it up into a rectangle and a triangle. Okay, this rectangle would be base of 1 times a height of 2, and that would be -2. So, and let's see if I can change the, I can't change the color of my pen. Sorry guys, well this one's going to be -2. And this is a triangle, and we'll say it's a base of 1 times a height of 2. So base times height divided by 2. That's a triangle, right? So the 2's cancel each other out, leaving us with 1. It'll be -1 because it's below the x-axis. So we got a rectangle with a base times height of -2 with a triangle with a base times height divided by 2 of -1. Then we got another triangle here. Okay, and after we find this one, we can put them all together. So this triangle is going to be a base of 2 times a height of 2. So we got 2 times 2, all divided by 2, because that's how you do base times height divided by 2, right? 2's cancel, leaving us with an area of 2. So we got an area of -2, -1, and 2. That would be the area all the way from -5 to -1, which is the area we're trying to find, right? So let's just put them all together. So we got -2 minus 1 plus 2, and that's going to be the -2 and the +2 can cancel each other out, leaving us with an area of -1. Okay, that's the exact area from -5 to -1. Let's do the next one, from -1 to 5. So from here all the way to over here. Okay, so we got a semicircle. Let's find this semicircle. It's going to be pi r squared. The radius is going to be, that's the center of the circle, the radius will be 2. So 2 squared, and since it's only half of a circle, divided by 2. Pi r squared divided by 2. That's going to leave us with 4 on top, and we can divide it by 2, so it's going to be 2 pi. That's the area of right here, 2 pi. And the area of this triangle right here would be base 2 times height 2 divided by 2 since it's a triangle. That's going to leave us with 2. So the area here is 2. Okay, so the area from -1 to 5 would just be 2 pi plus 2. And we can't put those together because they're not like terms, so that's our answer. 2 pi plus 2. Okay, now let's do -5 to 5. So the whole thing here. I'm going to do this one 2 different ways so you guys can see something, okay? So the first way is I'll just go through the whole thing here. -2 minus 1, -2 minus 1 plus 2 plus 2 pi plus 2. Okay, that leaves me with the -2 and the 2 can cancel each other out. So we got -1 and 2 make +1, so we got 2 pi plus 1. That's my area for the entire graph here. Now, I just did all the areas together. If you notice on this one, it goes from -5 to -1, and then this one picks up at -1 and goes all the way to 5, right? So what we could have done is we could have just done this area plus this area, -1 plus 2 pi plus 2, and that would actually be in parentheses because if that's a minus, it would distribute. In this case, we don't have to worry about that. The -1 and the 2 combined, making this 2 pi plus 1. Okay, and that gives us the same area as when we just added every single area up. So you can see these two integrals where it picks up, where this one leaves off, this one picks up, and it goes from -5 to 5. You can just put those together and it'll give you the area from -5 all the way to 5. Okay, that's one of the rules that we're going to be talking about on the next slide here. Okay, the next thing here, find the area from 2 to 2. This is another rule. Okay, the area from 2 to 2, that would be from here to here. Well, there is no area. You can't get an area from one lower, where the lower bound and the upper bound are the same. They're just going to give you an area of 0. Okay, so I'm going to show you 3 rules, okay, on the next slide here. And I've shown 2 of them right here very easily. If you go from a lower bound to an upper bound and it's the same number, the area is 0. The other one is that if one integral leaves off, the upper bound leaves off somewhere, and you find one that picks up at that same area on the lower bound, you can put them together to get that area from -5 to 5. So here are the rules. Okay, this is that first one I was talking about. If your integral is from the lower bound and the upper bound are the same, there's not going to be an area in between. It's going to be 0. Okay, this is that second one I was talking about. If the upper bound leaves off somewhere, like in this case it left off at b, and there's another integral that picks up where it left off, you can find the area from a to c by just putting these 2 integrals, adding them together, and that will give you the integral from a to c. And the last one is, okay, I don't know if you guys noticed this, but on every single integral we did, we went from a smaller number to a larger number, okay, of our function. If for some reason they flip that on you, so like let's say they go from ignore that equal sign, let's say they go from 5 to 1. Well, that counts from high to low, which we don't want it to be doing. So if you want to flip it so it reads correctly, like the way that I was showing you guys, from 1 to 5, you would just throw a negative in front of it, and you'd be good. So it's going to be equal to the negative area. So like this one's reading from B to A. We put a negative on the front, and it reads from A to B. Okay, and those are the 3 rules of integration that we'll be using throughout the Cal 1 test. So let's just try a couple more things. I have some absolute values on here that I want to look at. Oh, first let's do this. So we're going to use some of those rules. From 5 to negative 5. Now we already know this answer. We did it on the last slide. The answer was 2 pi plus 1. Yeah, that's what, when you figure out the area of all of them put together, it was 2 pi plus 1. We did that on the other slide. Now look at this though. It flipped them, right? So you know what? I'm going to say the area from negative 5 to 5 was of the function was 2 pi plus 1. Okay, I shouldn't have written that on this one. Okay, so if we flip them, okay, that's just going to make it negative. So we're going to have negative 2 pi plus 1. Or another way of thinking about that is negative 2 pi minus 1. That should be a minus 1, okay? And that's the area when you flip your bounds. And we just spoke about that. I'm going to go back real quick, so if you need to write that down, you can. I'm going to go back. That's what this rule's talking about. Yeah, if you flip the bounds, you just have the same area, but it's negative. Okay, going from negative 3 to 5. If you notice, that is reading backwards again, right? We need the smaller number on bottom. So we can make it negative, do negative 5 to negative 3 instead of our function. And our answer is just going to be negative. And then let's figure out the area from negative 5 to negative 3. From negative 5 to negative 3, well, before we figure out the area of this rectangle was negative 2, and this triangle was negative 1. So putting those together would make negative 3, right? And since we had a negative out in front because we had to switch the bounds, that makes this positive 3. Okay. I got some absolute values I want to show real quick, and this is the last slide. If you have an absolute value on the function like this means make everything on the graph positive. So like this right here, you won't be seeing it underneath, you'd be seeing it on top. And the 2 areas would be positive 2 and positive 1. And if I remember right, this one was 2, this was 2 pi, and this was 2. So if you're doing this one from negative 5 to negative 2, it would be from here to here. Okay, well, half of this triangle would just be 1, right? So if you ignore that 2, we're stopping right here. It'd be 1, right? So the answer to this would be 2 plus 1 plus 1, which is 4. Okay? Now, that's because the absolute value was on the function, so that made the whole function positive before we did the integral. Yeah, that makes sense. The absolute value is on the function, so we make the whole function positive before we do the integral. On this one over here, we do the integral first, and then we deal with the absolute values. So we do the integral, figure out what the integral is, and that means you can ignore all this. It's still below the x-axis when we're doing it like this. And then this will just make whatever integral we get positive. So let's do this one. From negative 5 to negative 2, it would be negative 2, negative 1, be negative 3, plus 1 would be negative 2. So the answer here is the absolute value of negative 2, and the absolute value of negative 2 is 2. So notice where you put these absolute values is very important. It will give you different answers. Okay? I mean, there's a possibility it could give you the same answer. But in this case, and many other cases, it will give you different answers. So you need to make sure if the absolute value is inside, that means you are making the function positive before doing the integral. If the absolute value is on the outside, you're doing the integral, and then you're making it positive. And that's this slide. I hope it wasn't too bad.